Hello and welcome back to our image and video processing class. We have seen very interesting effects that we can obtain in images just by doing these very simple local neighborhood operations. Let's use this video to see a couple of additional ones. In particular, we're going to talk about derivatives, how we implement those derivatives with local neighborhoods, and how important are those derivatives to do very interesting effects in images. So let's dive into that. Here we have a picture. It's a one-dimensional image that has flat, ramp, flat, and a very sharp jump and flat again. And let's see what happens when we take the derivatives of this. I have drawn this here, but before that, you might ask yourself, derivatives, that's a continuous operation. How can we implement that in our computer? There are many ways of doing that, but let me illustrate a very simple one. If I want to take the derivative of an image in the x direction, I can basically write that in discrete fashion as f at the pixel x plus 1 minus fx. Very simple. I just subtract two consecutive pixels. If I want to write the neighborhood operation, let's say in a 3x3, that will mean fx plus 1, I have a 1 here, minus fx, I have a minus 1 here, and every place else is 0. So that's basically how I represent that. I get a one-dimensional derivative in the x direction. Similarly, I can get a one-dimensional derivative in the y direction. So we see here the simulated values of this ramp, flat, jump, and flat. So we start with flat 6, we have a decreasing ramp, flat 1, and then a big jump. The first derivative is this first row that we see here. Very easy to compute. Following this operation, we have actually a couple of zeros because there is no derivative, the values are constant. Then basically we have a minus 1, minus 1. That means that the pixel values are decreasing in jumps, in constant jumps of 1. It's negative, so they are decreasing. And then once again we have flat, and then there's a big jump here. When we do 6 minus 1, we're going to get 5, and then it flattens out again. So we already see that considering the first derivative, we can understand that, for example, there is a ramp, a smooth decline of pixel values, and then there's a big jump. Very interesting. With a derivative, we can detect jumps as we expected. Then we can take actually the second derivative. And once again, we can write an explicit formula and a mask for the second derivative. So we're going to do the second derivative of our image. Once again, in the x direction. And once again, there are many ways of implementing this second derivative, but one of them is to take f at x plus 1 minus f at x minus 1 and subtract 2 times f at the actual pixel. And that's once again very simple to do with our ubiquitous 3x3. Now we have a minus 2 here, a 1 and a 1 on each one of the sides representing these two, and then we have 0 every place else. And if we do that, so that's kind of an additional derivative to the first derivative. It's a very simple exercise. We have to take derivatives of this. We could directly apply this to the original one if we want, but it's easier just to take, continuous pixel subtractions to the next one. And we see jumps when there are big changes. So 0 minus 0, it's 0. For example, minus 1 minus minus 1, once again 0. But when there are changes, we see a jump. We see 1 here, we see another here. So the second derivative very clearly marks when there are big changes in our image. And that's extremely powerful. We are detecting big changes by doing derivatives, which are, at least in their simplest fashion, implemented with masks like this one. So let's just continue with this and see some of the examples in a second. Here are different masks that compute different types of derivatives. So I'm going to ask you, look at this mask, for example, and tell me, what is this mask actually computing? Is it computing the third derivative, for example, in the x direction? Is it computing the third derivative in the y direction? Or is it computing the sum of the derivatives in the first derivatives in the x and y directions? Or is it computing the sum of the second derivatives in the x and the second derivative in the y direction? An interesting property. So what is this mask implementing? I thought that that wasn't too hard for you, so I gave you that as an exercise, but I just write it down. This is actually computing the sum of the second derivative in the x direction and the second derivative in the y direction. So this is computing the second derivative of f in the x direction plus the second derivative of f, I apologize, in the y direction. And that's basically, we know either from the previous slide, because we can compute the second derivative in x and the second derivative in y and add them. And we actually know that that's basically f at x plus 1 minus f at x minus 1 minus 2f at x. And I'm not writing the y's because they haven't changed. It should be at y, y, and y. And plus, so this was x, and now we're going to do y. That's f at y plus 1 plus f at y minus 1 minus 2 times f at y. And once again, all these are for a constant x. So all these are for a constant y, and all these are for a constant x. When we add them, we get this. And this is actually what's called the Laplacian of f. And we briefly talked about this when we were talking about the relationships between averaging and the Gaussian filtering and the heat equation. So this is what's called the Laplacian of the image, is the sum of the second derivatives in the x and in the y direction. These are different implementations of the Laplacian. Here, for example, we make the difference even stronger. We stretch it, and we're going to see the effects of that. The basic idea is that in the surrounding, basically we have one sign, and in the pixel we have a different sign, and we are basically computing in that way second derivatives. Just different implementations of this type of second derivatives. So what are the effects of this in an image? Very interesting. Here we see an image of the moon. What we see next in this image is the Laplacian. It's the second derivative in the x direction plus second derivative in the y direction. And we actually see it implemented with this. Here, we basically just stretch it. Remember, we know how to modify histograms, so we are stretching it. And what we are doing next is we are adding this to this. So we basically take an image, takes the Laplacian, we stretch it, and then we add them, and we get this image, which you can observe that is a bit sharper. Basically, some of the details are much more clear in this image than they were in this image. Now, we can actually make those details even more clear by computing a Laplacian that takes, in contrast with only a -4, a -8, so it actually stretches the differences even more. The process will be the same. We take the image, we compute the Laplacian with this, at every pixel. So every pixel is replaced by minus its own value and plus the values of the surrounding pixels. And then that we add to the original image. And look, we have a very sharp rendering of this image. You see a lot of details here that were very blurry here. Very simple operation. Image plus its Laplacian gives us a very, very nice effect. Many of these combinations can be done. And here we see another example for a different image. Again, an image that looks a bit blurry. We see once again its Laplacian. It might be hard to notice. All what we have done from here to here is once again to take second derivatives and then we add them. And look how much sharper this image is than this one. Much sharper image. We can see a lot of the details that were not very clear here by a very simple operation of adding the image to its Laplacian. And here we see basically what's called the Sobolev edges that are basically a different way of computing these derivatives. So very interesting effects in images by combining derivatives with the image in different directions, additions of derivatives, very interesting effects. One of those effects is what's called unsharp masking. It's a very famous concept, very simple. It's called unsharp masking. We have it here. The idea is very simple. You take the image and you smooth it out. For example, how can we smooth an image? We already know many ways of doing that. One of them is by doing local averages. So that corresponds to a mask, which is all ones, and 1/9, just to basically normalize. We do that, and then we subtract the original minus the blur image. Now, what's the mask corresponding to the original image? Very simple. A mask that does nothing has a 1 here and a 0 every place else. So original image is this mask, blur image is this mask. We take the differences. So it's this mask minus this will produce this. Remember, signs. So if I subtract from this, I will get a 0 in the middle, and I will get, basically I won't get a 0 if I normalize, but I will basically get 8/9 if I do the normalization, but a positive number, and every place else I will get minus 1/9, a negative number. That's kind of a derivative, as we saw before, kind of an implementation of derivatives in the horizontal and vertical direction combined. We take that result and we add it to the original image. And look what we have. We basically are enhancing the boundaries, as we have seen in the previous examples, that basically things become sharper, because what we managed to do with the blurring was reduce the boundaries, and then when we add that back, we get sharper boundaries and a very sharp image. And that's called unsharp masking. A very simple operation and very powerful as well. So I want to conclude this video in the next video by showing you once again inside MATLAB how we play with this type of operations of smoothing, adding images, very simple operations that produce very interesting effects in our images. So see you in the next video with the MATLAB demonstration.